we will start discussion of the implementation of the various broadcast abstractions. So let us look at the implementation of best effort broadcast. So we use a perfect channel abstraction, and whenever the application executes a BIP broadcast, we send the message M to all processes. This we can do in a for loop, and we are sending the message using the perfect link abstractions. So that's it. This is the implementation of best effort broadcast. Now let us look to the correctness properties of this implementation. If you remember, we had three conditions we have to satisfy: validity, no creation, and no duplication. And validity says if the sender is correct, all correct processes will deliver the message. If the sender does not crash, so every other correct processes will receive the message by the perfect link validity property. And therefore, every correct process receives the message, and that is validity. No creation and no duplication already guaranteed by the perfect links. So we have proved the correctness of the best ever broadcast. So now let us look to the implementation of a reliable broadcast abstraction in the fail-stop model. So what is the fail-stop model? We have again perfect links. We have the perfect failure detector abstraction P, and process fails by crashing. We are actually in the synchronous model. So these are the properties that we have. So here we give an overview of the lazy reliable broadcast. And the idea of lazy here is that if everything is all right and no process crashes, this will look exactly as the best effort broadcast. But if a process crashes, then extra work has to be done. So you do the extra work only if the process crashes. So what do we have? We have a perfect failure detector. And now to broadcast a message M, each process will do a best effort broadcast of the message. So that is the broadcasting process. At the receiving end, when a process gets a BIP deliver, so it saves the message and does reliable broadcast deliver higher up. So here we have BIP. Here we have the reliable broadcast. So if PI gets BIP deliver, it does an RB deliver. So that is fine. And here is a case where we have to do something different. So if a sender S crashes, we have to detect the crash and then relay the messages from S to all other processes. And we have two cases. We have the case when we get the message M from S, and then after that we detect the crash. In this case, we just redistribute the message, BIP broadcast it to everybody. But we have also another case we have to take care of, which is we first detect the crash, then later we get the message from the process, so we have to redistribute again. This can happen because the channels that send this information is not ordered, so messages can arrive in any arbitrary order. Whatever we do, we have to filter duplicates before we deliver. So this delivery should be done only one time. So we need to filter the duplicates. So let us look to especially the second case. The second case says if a sender crashes, so the sender is called S here, and we are at process PI. So PI detects the crash and then relays all the messages from S to all other processes. So let us look specifically to case 2. So So here is case 2. We have 3 processes. P1 broadcasts a message, and then P1 crashes. P3 will never get the message. But as you know, because of broadcast uses a perfect channel, then some of the processes might get the message and others do not. In this case, P3 did not get the message. Now, P2 first detects the crash, which is possible, and later on got the message. It was delivered to it. In this case, to guarantee reliability, P2 has to rebroadcast the message, to do a BEP broadcast to other processes, in this case to P3. So that's what it did here. So P2 broadcasted the pair or the tuple P1 and the message M, and then it is delivered here. So that is fine. This is case 2. So now let us look to the implementation in detail. So this is our component architecture. We have a reliable broadcast component with the interface broadcast and deliver. Then we have 2 components that are used by the reliable broadcast: the best ever broadcast component and the perfect failure detector component. And they are connected so that the perfect failure detector components has an indication event that is taken as input by the broadcast event. And also the BEP component has an output, which is a delivery event which becomes an input to the reliable broadcast component. So we cover this. And then a broadcast component, when it tries to send messages, it uses the best ever broadcast. So it is an indication from RB's point of view, and it's a request from the best ever broadcast point of view. So now let us look again to the implementation in detail, the algorithm. The lazy reliable broadcast, as we said, it uses a best ever broadcast abstraction or a component and the perfect failure detector component. We have a state here, so we have an initialization event which initializes the state of this component. So the first thing is the delivery set. It's called delivered, and this set is there to remember which messages that has been delivered to the application. Then we have the set of all processes. In fact, this is a set of all correct processes. Initially it is pi, that is a fixed set. And then we have an array or a map indexed by each process, and it is a storage for saved messages. Initially, for each process, the set is empty, but whenever there are value here, so it says I have received a number of messages from process I, and that will be stored there. So now, when the broadcast component gets a broadcast request, gets a broadcast event here, then it just triggers a best ever broadcast with here a triple tagged by data. It includes its identity self here, that means the identity of that process. So if this process PI, self will be PI, and that is the message. So now when we get a crash event, so this is saying that PI has crashed, we remove PI from the set of correct processes, and then for each element in the set of PI from, this is like a message that has been sent from PI, we trigger a best ever broadcast with the message, the original sender, included. So this is redistribute everything when we have a failed process or a node. Now let us look to what happened when we get a best ever broadcast delivery from process PI with this message, the sender and the message. So if the message is already delivered, we do nothing. But if it is not delivered, then what we should do is try to avoid duplicate. That's why we add the message to the delivered set. We record that we received this message from process PI. This is stored for future use in case PI crashes. And then we trigger reliable broadcast delivery for this message from that source. And then we check if PI is faulty or it is correct. If PI has crashed, we resend the message to all other processes using a best ever broadcast. Now we have seen an execution scenario for case 2, where we first get and detect a crash of process PI, and later we get a message. Now let us look to the first case, an execution scenario of the first case, where first we get the crash, and then after that we send all the messages that we have stored for PI, we resend them, redistribute them. So here is this case, which is case 1. What does it say? So P1 broadcasts the message and then crashes. The message is delivered to P2, and then we detect the crash here. This is the delivery, this is the crash, and now we rebroadcast everything from P1, from the source, and this source in this case is P1, and that is the delivery here. So now we prove the correctness of the lazy reliable broadcast. First, to note that reliable broadcast validity, no duplication, and no creation are satisfied by the best ever broadcast property. In particular, reliable broadcast validity, which says if a correct process broadcasts the message, it will deliver the message, is satisfied by the BEP broadcast validity. Now we need to prove the reliable broadcast agreement property, which is RB4, which says if a correct process delivers a message M, then every correct process will deliver the message M. And to prove this, we assume that we have a correct process that delivers the message M, and we try to prove that every correct process delivers the message M. So let us assume that PK is our correct process, and it delivered the message that has been broadcast by PI. So now we look to PI, and we have two cases. Either PI is correct or PI has crashed. If PI is correct, then by the validity property of the best ever broadcast, PI also ensures the correct delivery to every other process. So therefore, every other process will deliver the message. Now, if PI has crashed, then PK will eventually detect the crash, that is completeness of the failure detector. So we have used now the completeness property of the failure detector. And because PK detects the crash and PK is correct, PK is going to BEP broadcast the message to all processes, and by the validity property of BEP broadcast, every correct process will get the message.